Hello YouTube. I'm going to talk about the magnetization, um, and I'm going to talk about how you study the property of a material to be magnetic or not magnetic. Um, it's not really hard, and I'm going to explain it. So let's switch scene. Wow, so much details. Um, okay, so what I've um, shown is an axis with H as a lateral as the horizontal line. H is the excitation magnetic. It means that you will put an external magnetic field around the material you want to study. So basically at zero, it's the use that you will get of the material. M on the other side is the aimantation. Um, is the aimantation. It's usually a vector, but obviously it's norm. Um, uh, yes, and it represents the property of a material to generate a magnetic field around it. Um, so we will study that. So first what you're going to do is study the material demagnetized. Sometimes you will not find it demagnetized, so the curve will start either at 0, 0 or slightly above or below. 0, 0 means that if you demagnetize it and if you don't put anything around it, don't put any magnetic field, it will not um, it will not create any magnetic field. So then you will increase the magnetic field around it. So the spins of the atoms will start to be reoriented. So how it works is you have an atom and you have electrons that are around it. Obviously, for this study, we will neglect the atom on itself. We'll just concentrate on the electrons around it. And statistically, for a non-permanent magnet, it's random. The position can either be upward or downward, so it doesn't matter the direction of space. Um, a permanent magnet is just a magnet that you use. I don't know if I have any. Yeah, it's just a regular magnet. It's called a permanent magnet, meaning that it's a magnet no matter what you put externally, um, and in opposition to electromagnet that you need to put electricity in it to create a magnetic field. So yeah, for what was I saying? Yes, so you will start to reorganize the spins of each the local repartition of the aimantation vector. So instead, since they are in every direction of space, they will slowly start to reorientate in direction of the magnetic field H. You will put a magnetic field in a direction, for example this one, and all the magnetic field will slowly start to reorientate in the same direction. So what will happen is this. Okay, it's kind of ugly, but you see it's a growth, and that will happen. But at some point, all the spins will be oriented in the same way as H. So they will be all in this direction, for example. And as you'll see, no matter how much you put external magnetic field, it will not reorientate the material. So what will happen is just this. It's called saturation. Well, in fact, what happens is that you can't take a measure of M since it's not defined after H. So it's called saturation. So I'll just put an S around it. So it's called saturation. And basically what will happen is that you can't go above. All the spins are aligned in the same direction. Okay, so this curve is called the curve of first aimantation in French, but I don't know if aimantation is actual word in English. And then what you will try to do um, is lower the external magnetic field H to see what happens. And since you have already aligned, it will just slowly fade out like this. Okay, so you have all the spins aligned, but the external magnetic field H will diminish. So some will stay in their own spin, in their own aimantation, dipolar orientation, but some will tend to come back to their original position or be random, or doesn't matter. So you will reach this point at h equals 0, called called the point MR for aimantation remnant. MR, I think it's called like this in English too. So it's the point for h equals 0, and that's what um, is left after you magnetize the material. So for example, for a permanent magnet, so what you call usually a magnet, MR will be very high because you'll have a thing that produces magnetic field without any magnetic field around it. Then you will start to diminish, to lower the H again, but in the other sense. So you will put a magnetic field on the other on the reverse sense. So it will lower like this. Okay, and then you will reach this point. It's called the coercitive excitation. It's named HC, 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 and then it's just a value. I honestly I don't know what it's used for. I have no clue. But maybe for calculus, for example, if someone asks you, hey, what's the coercitive excitation of this material, knowing it's a curve of magnetization, you will get that. And then by symmetry, you'll pretty much get what happens. So you'll reach a saturation again, S, and you'll go on the other sense again. You'll reach minus mr, oui. Okay, then you'll reach the other side. So this was minus IHC and this was HC. Okay, and then you'll come back to saturation again. And that's actually how you study magnets. But there is something to differentiate many magnets. You will call it either soft or hard magnetic materials. So yeah, milieu doux or milieu dur in French. So it depends if you can approximate the curve. Since MR and HC depends on the material, you'll get either something very large in terms of surface. For example, if I do this you see it's a very large area. But then if I draw another curve where it's more like, well, not this, not like this. Okay, where is it? This. If I draw something more like this to this, it's more like a linear expression. So this is for soft material, and you will approximate this line by calling it soft, and say that B in the theorem of um, many theorems that use magnetic fields, you'll approximate B as mu 0 times h, since it's a curve like this, and times mu r, which is a value that is relevant to how the magnetic material reacts. So you will actually say that this is equivalent to a big curve like this of equation, can I say it, mu 0 mu r. Yeah, that's all. So I guess it's pretty much done for this. I know it's pretty ugly, but I am not a graphist. If you have questions, feel free to ask them. I'll be glad to answer. Um, yeah, drop a thumbs, no matter if it's upward, downwards, with how it's polarized on space. Yeah, thanks for watching. Bye.